Joe's head. And now if I just stack them up, according to the angle that I took the projections, right? So maybe I have really dense, not dense, dense, really dense, not dense, really. People get me like this? Okay? So I just stack the projections. The amazing thing is that if I take the 2D Fourier transform, what is the 2D Fourier transform? It's the Fourier transform in this way and then this way. That's all it is. I will actually get a picture of what's inside his head. Totally amazing, right? It's a miracle, and it's the miracle of tomography. Okay? And so this is what allows you to make these unbelievably detailed images of the inside of people's heads. Is this basic idea of Fourier transforms that you've been learning about in this class. And it's very, very, very powerful, and it's going to become only more important through time. Okay? The neat thing, though, is that this same idea of shooting things through his head also applies to shooting things rather than projecting through his head, you can also reflect waves from things. And so this is exactly the same way that sonar works. Okay, in a boat, when you send a sound wave right down into the water, it bounces off things and comes back and is acquired by some array of microphones in the water. It's the same way that radar is able to make a picture of the Earth or a picture of Venus through the clouds. Okay? And it's the exact same way that we make these pictures of the underground to look for oil. It's all the miracle of tomography. And that's the beauty of DSP, is one idea, projections give you Fourier transform slices, underlies all of these techniques. Right? So study Fourier transform really hard, become an expert, because then you can do all of these things. Okay? So that's imaging. Very, very important. Very, very, very important. Okay. Another neat aspect of imaging is moving away from making two-dimensional images to three-dimensional and four-dimensional images. So just to give you an idea, let's say that we want to understand which parts of your brain control different things in your body. Okay? Then you can do an experiment called functional MRI. We've heard of functional MRI. Okay, this is very important. Okay? Cutting edge kind of idea. Here's an experiment, and this is not made up. Imagine we did the same experiment with Dr. Doe. Here's his brain. Very smart. Look at that. Wow. Dense. Very dense tissue. Good. Say we did this same experiment with Dr. Doe, but as we took the picture, we asked him to wiggle his finger. Or wiggle your finger while we're doing this. So he's wiggling his finger. And then imagine we don't do this once, but imagine we do it once every second. Or many times every second. Okay? And now imagine if we look at one particular spot in his brain, right? And this is what that value looks like, but now over time. Does everybody get it? Okay? And what we can do is we can actually do convolution. Who knows convolution? Okay? Convolution with his wiggling. And the neat thing is, this is without him wiggling, this is with wiggling, and you can clearly see that if we do a convolution here, we're basically matching up, right, the wiggling of his finger with the actual changes going on inside his brain. Okay? And what you can actually show is that you can detect activity of different sorts inside people's brains. You can tell them a joke, make them laugh, and figure out which parts of their brain are making them laugh. Okay? You can make them do mathematics. 16 times 3.
28.
Okay. You can see what part of the brain does mathematics. Okay? Unbelievably important, not only to understand how the brain works, but also for things like surgery. If you need to remove, say someone has a brain tumor, some cancer, and you need to remove part of their brain, you can do experiments like this, even during the operation, to understand what is happening as you're doing the operation. Okay? So very exciting, very important. And this particular problem you can see is three-dimensional, because we have 2 dimensions here of space, and one of time. But now if you imagine, this is real, this is mid-node brain. When we told him to add 16 and 12, and you see the price of lights out there. Okay? But doing it in 3D, now this is 4-dimensional data. Because what we're doing is we're taking scans in 3 dimensions of the whole head, but what we're doing is we're also looking through time. So we get 3 space dimensions, 1 time dimension, and we're actually finding how parts of the brain react. Okay? Do you believe me that this is really true? Seems crazy, doesn't it? But it's totally true. Okay, so that's tomography. The interesting thing is the same idea of this idea here of correlating, okay, or convolving with signals that you're looking for. Okay? Did you talk about match filtering? You're going to. But this whole idea of convolving with signals that you're interested in order to look for them, because the smooth curve is the information, this curve is the data, right? You're trying to pull the information out of the data. The same idea applies on the internet as well. So now if you think in terms of the internet, does anybody know what the internet is? Okay, you know what the internet is. So you have a computer in Hanoi, and then you have a computer in Illinois. What was Ryan? Are there a lot of Vietnamese in Illinois?
Yep.
Okay.
More than 1,000.
Okay. Or Ryan, yeah, because it rhymes. That's probably why they went there, right? Okay. So New York City, Ho Chi Minh City. Wow, it's amazing, actually. Okay. He's the only one who gets my jokes. Okay, so the same idea of projecting through. Remember that we projected through Dr. Doe's head to find out what's going on inside. The same idea of tomography can apply on the internet. So you could start sending some packets from Hanoi, and you could send those packets through to Illinois. But then you could also send packets from Ho Chi Minh City up here to Houston. Okay? And you could also send packets from Moscow to Buenos Aires. You see what we're doing? We're going through the internet through different paths. Right? Well, the amazing thing is, the same kind of miracle happens here. You can actually make maps of what's going on inside the internet. Where there's lots of traffic, where there's not a lot of traffic. It's slightly different mathematics because it's more nonlinear than linear, but the exact same ideas apply. And this is fundamental to many problems in computer security, things like in machine control, figuring out if you're going to stream voice over IP, where is the best place to stream it. These tomography ideas are used in a lot of different areas. Okay? So that's for the power of tomography. So now let's talk about an example that's again related to tomography. Sort of like my whole talk is about tomography. But this is about camera arrays. So everyone knows what a camera is. But now the question is, what can we do with a whole bunch of cameras? And we can do very interesting things. So what we can do is we can take pictures of objects from multiple different directions. Okay? And we can use this to do a bunch of things. One, to recognize people. Okay? Another possibility is for things like 3-dimensional television. Imagine television. How does television work now? Right? Or movies. They're 2-dimensional. There's a camera at a certain point, and there's actors, right, or a scene, and then they broadcast that exact view, right, to your television. So really, when you watch TV, or through here, for example, over there, it's no different than if your eye, right, looking at your television, is the same as the cameraman's eye right now. Everybody gets the idea. So basically, it's though you were right there. But what if you want to look from a different angle? What if you're in a movie and you don't want to look at the actors this way, you want to look at the actors this way? Okay? Well, very soon, there are going to be systems where you'll be able to zoom and pan around the entire movie scene because they're going to have multiple cameras set up around the scene in order to be able to do this kind of thing. Okay? And this is already used in movies for special effects. Does anybody know what movie was the famous first movie they did this? The Matrix. How many people saw the movie The Matrix? Okay? So when they jump up in the air and it's like they're frozen in time and the camera spins around, that's actually done with a gantry of 32 or 60 cameras where they actually are